All right. Thank you very much. Thanks to the organizers for the opportunity to present this little update here. I choose to use my 15 minutes of talking time as a little advertisement, namely for an update to the software that I also briefly spoke about during last AFA. Let me just to remind the people that have been there, or also introduce to the ones that have not, what exactly my software does and what this is about. This is about bounded error terms. So basically imagine big O terms, but with an explicit constant. A practical example is right here. So you can imagine that this term here, b of 2025 n to the power of 5, with this little index of n greater or equal to 42. This describes functions that are bounded in absolute value as soon as n is greater or equal to 42, bounded by 2025 n to the power of 5, right? So if you would replace this with a big O term, then what would you write instead? Yeah, just big O of n to the 5, right? It's easy so far, okay? Good. The good news is that basic support for arithmetic with these is already included in SageMath. Namely, as a practical example, and this requires some thinking, which is why I like to do it that way. The first line here basically is just the definition of the structure that contains these little creatures, a so-called asymptotic ring. You've seen a bunch of these throughout my talks over the past few AFAs, but just to show you this here. So you generate one of these rings, then you take 2n and we subtract a b term, which you can generate by calling the asymptotic ring and the big capital B method on it. And you ask it, give me a b term of 2n that's valid from 42, and you add these two together and you get, which is maybe not that far from what you would imagined, a b term of 4n, which is valid from n greater or equal to 42, right? Okay, let's make it a little bit more complicated. The next two lines have a second example, and actually I've also spoiled the explanation already below that. If we try to add an explicit term here, which is 1 over n, and a term which is just 2n, then what would need to happen? Well, actually, we need to do some sort of estimate to be able to have this guy here absorb this guy over there. And what happens basically is that 1 over n is internally written as n over n squared. And then the bound that we have for the validity of the estimate, this is used to estimate away the denominator. So in this case, we could replace this 1 over n by n over 10 squared, which is 100th times n. And so the result of adding these two guys is a b term which has 201 in the numerator, 100 in the denominator, and still times n. So linear b term and so on and so forth. You see already that arithmetic with these, especially if it's not just two simple terms, is a little bit weird and maybe a little bit complicated. Anyhow, let's make it more complicated. The extension package that I've talked about last year, dependent b terms, you can find the code on GitHub. And if you'd like to follow along or play around with it later, there's a QR code over there, or this little link over here, which you could just enter, and then you get an interactive thing where you can play around with the software. I'll actually also do something very, very adventurous and try to click on this here. We'll see whether it starts up in time before I finish my talk. You can install the package quite easily, and the feature that is added by this extra package is that it allows you to add an additional, which are called dependent variable, which depends on the asymptotic variable n in some case. Plus, it also has some additional extra tools for dealing with quantified Taylor expansion and so on and so forth. Now, that was basically what was the status quo at AFA 2024, and I'd like to, need to click here again, sorry. I'd like to show, before I show what's new, let's do another exercise, and this time it's a little bit more complicated because this time we have the additional variable in it as well. So the b term, the variable is bounded below by 1 and from above by n to the 4/7. Then we have this little fraction here, which is an exact term, and we have this bounded term on the right. And now I would like you to work out the answer. I'll give you a second or two. Actually, the computer is much better than doing this sort of stuff. So let's just ask the computer. The package is used like this. You import it. You use this special asymptotic ring that comes with the package. You define it in a fairly similar way. The details are not that important right now, but in the end, you can specify the exact term as is written up here. You can specify this b term, which is over here. And if you combine these two, then it will say it's 3,373 over 1,000 times the absolute value of k squared times n to the minus 3, valid from n greater equal to 10. So it managed to absorb the explicit term on the left into the term to the right. And now actually I should maybe say a little bit more how this worked. Miklos said earlier that every talk should have a little proof. I suppose that this is my proof in this case here. The first thing that happens is the software checks whether the exact term can be absorbed into this O term, which it can in this case. You need to work with fractions a little bit, which is particularly devious in this case. So I've done it here for you. The exact term is small enough to be absorbed by the B term. And then, well, we have to do some sort of estimates on how this is done exactly. And in this case here, what happens is, well, we use some very, very crude methods. We just throw together everything in some sense, and then get a bound for the exact term that we can directly pull into the B term. And then there's some rounding going on as well, which is why this constant here is so nice. Otherwise, there would be some weird square root or fraction or whatever. Not very nice expression. So yeah, this is what the package basically does. And now I actually would like to tell you what's new since LVA 2024. So we've used this we've used this in the context of showing some inequalities where standard expansions would just give you O terms, and we would like to actually have inequalities for all n without saying that eventually the inequality will hold. We would like to prove that the inequality actually holds for all n. Then exactly. So the one thing that I've added since then is there's now support for scaled monomial growth. I'll show you an example of why this is really useful on the next slide. Then there's a funny thing. Namely, at the time of when the abstract for the talk was due, I was working on a problem where I thought like, well, this would be really nice if the package could just do Euler-Maclaurin summation. And I actually worked out a bunch of details, but then I moved away from the idea of using Euler-Maclaurin summation in my problem. And so I didn't need to write the code, which also means that now I don't have the feature to show right now. But the details are already worked out, so I'll eventually implement this, I'm pretty sure. I'll show you some of the things that I've thought about on the later slide as well. And two other things that are kind of nice, I guess, is there's some improved robustness in terms of which functions you can compute Taylor expansions for. And it's also much better, much faster. I mean, much faster. It's like a factor of 2.5 or something like that. So it's fine, I guess. Computation of our large example didn't take 4 minutes anymore, just 1.3 minutes, which is, well, okay. An application of where this scaled monomial growth was really useful was a problem by Ramarian, specified in question 294, the more or less well-known Q function, which is actually this pair of functions here, Q and R, that you can see. And the question that is posed by Ramarian was that the difference of these two functions should be shown to follow an asymptotic expansion of this shape, where this theta here is a quantity that is bounded explicitly between 2/21 and 8/45. This is, in some sense, a comprehensive toy example because it has been studied extensively by Ramanian, Watson, Knuth, and already completely solved by Flageolet, Grabner, Kirchhoff, and Prodinger. And the nice thing is that while they used a very nice approach using a specific integral representation of the difference of these two functions, you can also do it by brute force, more or less. When I say more or less, because you still need to be somewhat careful with the actual estimates that you do, that you feed into our program, and then the rest of the things happen mechanically. So you will notice that I say mechanically and not automatically. I would like to have it automatically, but that's not really possible right now. The sketch is more or less, you represent the difference as this sort of sum, and in the middle and large range, which is the range where k in this summation is greater or equal to some constant times n to the alpha. In our case, actually, what worked out well was c equals 4 and alpha is 3/5. We can estimate this with an exponential term and then use an integral bound to obtain this particular b term. It's a little bit small, I'm sorry, but it's also not that important. You just notice that this number here is really, really tiny. It says 3.11 times 10 to the minus 31 times n to the minus 10 is the actual bound of the error in this region. And this needed to be very small because actually this value of theta here, well, actually, I'll show you in here. This value of theta here, the exact expansion, looks more or less like this. And for a value of n, which is already somewhat large, namely larger than 70,000, this quantity here is already pretty small. So in order to show that the error that we get is even smaller than this, we need to go very, very, very small. And actually, I'll spoil a little secret. The actual quantity that we managed to obtain is not even small enough to show that this here is small. We managed to show the upper bound, but for the lower bound, we need an additional argument of monotonicity on theta. The one thing that I'd just like to touch briefly on, the Euler-Maclaurin summation is, well, the more or less well-known formulas are here. You can represent the difference between the integral and the sum of a function of a given range by quantities that involve sums of Bernoulli, of values of the derivative scaled by the Bernoulli numbers, and an error term that involves the Bernoulli polynomials. And the trick in this case is, and this makes it a little bit complicated to compute because you need to be able to provide estimates on the function and its derivatives in some sense, and that's the part that I would like to have more automatic than it is possible currently. So that's the reason why it doesn't work right now. But if you rewrite this error in the integral as a difference between the integral over the entire domain and subtract the infinite part, then you can actually get that the error is some constant plus something that decays if the expansion order is large enough. And while this means that the constant term in the expansion is tainted in some sense, you can't really get it, you can't really express it, we can throw that out or at least replace it with an unknown constant and get the rest of the expansion in a precise way. So this is possible. One thing that I would like to add in this context, actually, I have a bunch of textbook examples that I use for testing my code. But if you have fun, whatever that may mean, fun toy examples, let me know. That would be pretty great. And that's it. Thanks.
Thank you. Question.